Hello, Algebra 2 students. Today is going to seem a little bit different in that for day 5, we were talking about polynomial identities. So, something to keep in mind, what an identity is in the first place. Identity, making up my own spellings there. It's the idea that an expression or an equation, maybe more appropriately, is true regardless of the x value. So what I want to do to start is I want to show you the difference between something that's considered an identity and then not an identity. Right, so under the identity column, the first little example I could give you is to say that x squared minus 9 is equal to x plus 3 times x minus 3. Right? And now that's actually a fact that you would recognize that, all right, well, yeah, when I factor this binomial, it turns into difference of squares, so x plus 3, x minus 3. But the reason that that actually works is that it's true regardless of the x value. So as in a little example, if I said, let's let, x equal 1, and I plug 1 in on the left and I plug 1 in on the right. So 1 squared minus 9, and then 1 plus 3 and 1 minus 3. Well, 1 squared minus 9 would give me negative 8. And then 1 plus 3 would give me 4. This would give me negative 2. That comes out to be negative 8. So I just picked a random x value and it worked. And it's a true identity if no matter what x value I pick, it will always come out equal. So if you pick, any other value, I'm going to pick something simple. If I say, let's pick 4, and I do 4 squared minus 9, and then plug in 4 here and here, I'd get 4 plus 3 and 4 minus 3. So 16 minus 9 would give me 7. This is 7 times 1, and there we go. Right? So the idea is when it's an identity, you could play this game all day long. You could put any value you want in there, and the two sides will always be equal. So when I say an equation is true, I mean that it literally both sides come out equal to one another, regardless of what x value you plug in. Something that's not an identity would be if I said, 2x plus 7 and then equals 12. Both sides of this equation are not always going to be equal. If we said, all right, well, let's go ahead and solve this thing, we could do 2x, oops, not z, and we could subtract the 7 and get 5, and we'd get 2.5, which what that actually means is that, all right, both sides will be equal if I plug in 2.5, and so that would come back to be 5 plus 7, so I would get 12 equals 12. But if I plug in any other value other than 2.5, those two sides are not going to be balanced. So like if I throw in a 1 there, I'm pretty sure I don't really need to convince you, but I would get 9 on this side, 12 on this side. They're not coming out equal. So when something's an identity, I can plug in any value of x or whatever variable I have, and it will always match on both sides, versus this here is not an identity. All right, with that being said, to be able to prove that something is an identity, because that's the key of what we're looking at here. All right. So to prove or to show is typically how it's worded, that expressions are identities, meaning that they're going to be the same all the time. We would want to not plug in any values for x. All right. So you just keep the variables that you have, meaning don't sub in anything, because I don't want to show that it only works for those two examples. I want to show it works for everything. So I'm going to keep that. And then your options is that you can either multiply out one or possibly both sides of the equation to show they're equal, or on the rare occasion, you could work the opposite direction. You could possibly factor one or both sides to show that they're the same. So sorry for my shorthand there. I tend to leave words out. Okay. One key rule, star it right here because it's easy to miss this, is that if you're trying to show that like the left-hand side of the equation is equal to the right-hand side, you're not allowed to move things across the equal sign. We're not solving. That's a different idea. So do not move terms across the equal sign. So do not move terms across the equal sign. Get rid of that little guy right there. Or I can't. There we go. All right. So let me show you what I mean. If we go back to the example that I used in identity, oops, I'm getting more and more crooked. There we go. So if we revisit this guy, the x squared minus 9, saying that that is always equal to x minus 3 and x plus 3. Your options would be, think about this as a barrier. We're not moving across it. So I can either multiply this side out, which means you can do box multiplication. You can do a little FOIL. So we could go, x squared and minus 3x, and then plus 3x and minus 9 to show that, yep, indeed, it works out. And so when you get to the end and you're able to say like, hey, they're equal, we usually just put a little check mark or something to say like, I've done it. Good job for me. Right? Or if it is something that is factorable, because it won't always be. But if you do know how to factor it, you could, in fact, say, all right, let me factor this side. And you can break it into, x plus 3 and x minus 3. And then just simply bring this down and say, ta-da, I've done it. Right? So that's kind of the two approaches that you can possibly take. But notice how I never, added 9 over, did anything like that. Keep them separate and just show that they are the same thing. All right, I am slightly out of space. I'm going to hop on over to the next page. If you have more room, you can stay where you're at. We just have a couple more examples to look at. So for number 2, then I want to give you x minus 3 and times x squared plus 3x plus 9. Show that that is equivalent to x cubed minus 27. Now I'm hoping as you look at it, that something looks a little familiar about that. But if for any chance it doesn't, or you're not sure how you would show this otherwise, let's multiply it out. This is a great one rather than trying to extend foiling to actually use that box method for. So let's multiply our way through. Here's x cubed, 3x squared, and 9x. In that second row, minus 3x squared. And then, oops, just kidding, minus 9x, you keep going. And minus 27. And then when we go to combine our like terms, there's that x cubed, minus 3x squared and plus 3x squared will cancel. Same argument goes for the minus 9x and plus 9x, and then minus 27. So as long as you can adequately show that those two sides are equal, that's it. That's all you have to do to be able to show that they are an identity. So this is always equivalent to this regardless of the x value. We got one last one to try that's going to look a little bit beyond the ones that we were just checking out here. So for this last one, if we take a look, I've got a squared plus b squared, and then times x squared plus y squared. Show that that's equal to a x minus by squared plus, wait for it, it's coming, bx plus ay squared. All right, there's a lot going on there. The fact that my direction to you is to show that it's an identity is code for, okay, this better work out. Sometimes the question will say, prove whether or not it's an identity. And in that case, you have to expand everything out and then determine, did it come out the same or not? So for ones like this, I would say let's multiply out the left and the right-hand side so that we can see what's going on here. Because we did foiling ones, let's try it one more time. So FOIL, remember, first, outside, inside, last. So the first term would be a squared x squared, outsides plus a squared y squared, insides plus b squared x squared, and then last plus b squared y squared. Those are all different terms. There's nothing we can combine there. Let's see what happens on the other side and compare the two. So for this one, you're going to be multiplying this by itself. You're going to be multiplying this guy by itself. Because I foiled here, maybe I'll go box method here so that we make everybody a little bit happy. So ax minus by times another ax minus by. So a squared x squared. All right, minus, this is going to be abxy. And you can list those in any order you want, but I like that order. Here, minus another abxy. And then lastly, plus b squared y squared. All right, to those four terms, we are going to be adding over here bx plus ay times another bx plus ay. All right, stay with me. We've got b squared x squared, a b x y. It helps if you write them in the same order every time. And another a b x y, and then lastly a squared y squared. All right, if I take a look at what I've got, first term here, a squared x squared. This is going to give me 2, so minus 2 of these a, b, x, y, and then plus b squared, y squared. Over here, I've got plus b squared, x squared. These two together give me 2abxy, and then I'm going to squeeze in that last a squared y squared. All right, hopefully you're already starting to see that this minus 2abxy and this plus 2abxy, those are going to go. And then what I'm left with is just 4 terms. So a squared, x squared, b squared, y squared, b squared, x squared, and then lastly, a squared, y squared. Well, even though they're in a slightly different order, if I bring these down, here's my a squared, x squared, so these two match. Next up, I had a squared, y squared, so it matches with that one. B squared, x squared, these two match. And then last, b squared, y squared, and there we go. So you don't really have to show 8 check marks, but if it helps you keep things in order, awesome. So what we've shown is that the expression on the left is equal to the expression on the right. So this crazy thing to start is an identity because those two sides are always going to be equivalent. All right, that is it for now. Make sure you've answered the video questions. See you guys soon.